Well, hello, everyone. I'm currently the only one in this short little conference we've got going today. Um, what I'm going to do is try to make up for the fact that we did not have a good recording last time. For some reason, it did not. Hi, Zach. You're here with me, aren't you? Can you hear me? That's good. Yeah. I've got it recorded. We're going to see if we can do this. Yeah. Hopefully, the the folks over at the tech support group will help us upload it into YouTube. So let's see if we can run through a few things that we needed to cover. So I'm going to share a screen with you. And you can see that we have Kellogg's revenue. Let me go ahead and put the date in on that column heading. Not the state, but the date. So I've got Kellogg's revenue. I also created 4 seasonal dummy variables. And I've got something called seasons. I'll tell you where that came from. Then I have employed people and interest rates. And I've got forecasts for each of those. So let's start with the fact that we can record events relative to this time series. They don't have to have continuous numerical values like the Y variable for Kellogg's revenue or the employed people for instance, of the fourth quarter of 1992. It's got an incidence of employed people, but something else could have occurred. And since it's a fourth quarter, I'm saying, hey, the fourth quarter occurred during that time. Same thing for the first quarter. We have values for each of the variables for the first quarter of 92, but I'm going to say that Q1 is an event that occurred then. So if we do that for the first quarter, second quarter, you can see that 1 follows under the column of Q2, and the third quarter, 1 appears there, and the fourth quarter, 1 appears there. What we've done is we've created a series of events that are related to the dates, nothing else. And we can capture that in terms of seasonality, right? Because seasonal effects are different per quarter. Okay, and the seasonal effects repeat year after year. So that's what I did is I created this first diagonal of 1s and 0s, 1s diagonal, 0s across, beginning with the first quarter. That's where the 1 begins, and ending in the fourth quarter, where the 1 ends in the fourth quarter. And then I just selected it and copied it and pasted it below it. Copied that, or I just pasted again. I didn't have to copy again. So forth and so on until I got the entire data series, all the dates covered with quarterly events. And you'll notice that the first quarter is always synced up with the first quarter date, right? So whatever happened there relative to seasonality, for the first quarter, we ought to be able to pick it up and create a coefficient that'll help us forecast the first quarter for every period. And the same thing for the second quarter. It appears at the same time. Anyway, the whole smear is filled out all the way until the last quarter, the fourth quarter of 2017. Then I took the leftover values, repeated values, and I created a forecast for those. And let me show you the forecast. I don't have the fourth quarter forecast because I left it out. but the first quarter is here. That's not the Q1 forecast, is it? Let me go get this is a forecast for something else. Just put the dates in so we don't get anything confused here. Let me slide this over so you can see. Just put the dates. Tied at forecast dates. Okay. This is 3/31/2018. See if I get the 31s in the 6/30/2018. 9/30/2018. So I can make sure I get the quarters lined up. 12/31/2018. I've got a comma instead of a cotton picking slash. There we go. So we do the 3/31/2019 and put the next date in 6/30/2019. 9/30/2019. And last but not, okay, messed up again. Got too many 30s in there, don't I? Last but not least, 12/31/2019. Hopefully we got it right. Okay, so if this is the first quarter, the 1 belongs there for first quarter for the forecast. This is not a first quarter, so 0 belongs there. This is not a first quarter. This is not a first quarter. This is a first quarter. This is not a first quarter. This is not a first quarter, and neither is that. So we're cool there. Second quarter. This is not a second quarter. Second quarter appears here. And that's the first quarter, so that should be a 0. And this is the second quarter, right? For the forecast period. 0/0. Should be a 0 here too. So we got a Q1 and another Q1. We've got a Q2 and another Q2. Now we need a Q3. I don't know how this forecast gets screwed up. This is a Q3. And this is a Q3 right here. And the Q4s we don't need because I left them out. Okay. And I'm going to nuke recession forecast. Delete cells for the time being. Okay. So we have forecast values, first, second, and third quarters. I left the fourth quarter out, so it's all 0s, and still first, second, third quarter forecasts for the forecast period. So these, whatever coefficients these are calculated relative to these dates for seasonality, they'll be expressed going forward as the forecast values. And I've taken the liberty of forecasting employed people, okay, and interest rates. And let's see what kind of base model we have if we run regression. Stat, time series, not time series, stat regression, fit regression model. We want to put the company's revenue in as the response variable, that it responds to employed people and interest rates. Okay, let's see what happens when we do that. The F statistic's reasonably high. The R-square value is above 50%. We're looking at 78%. Let's just pull this down so we can see some more stuff. The VIFs are low, and the t-values are high. Okay, and the interest rate's negative. It's a negative relationship between interest rates and Kellogg's. And employed people, there's a positive relationship in this equation, okay? Because the negativity has been picked up by the interest rates. And we have something called a Durbin-Watson statistic down here. And the way I got that is before I ran the model, stat, time series, or regression, excuse me, regression, fit regression model, you go to results. And you make sure that this Durbin-Watson box is checked, because typically it's unchecked. The reason why it's unchecked is because they don't expect you to use time series analysis for regression. This Durbin-Watson statistic deals directly with time series. And as I mentioned the last class that we had, the Durbin-Watson statistic is very much a substitute for the chi-square statistic that we looked at in ARIMA and the LBQ values, because it tells you whether or not you've got positive or negative serial correlation. And what I need to do is get the table out, and I can show you what that means. Let me see if I can find a Durbin-Watson statistic table. I just need to find the regression slides. Which for some reason are eluding me. Okay, here we go. Let me show you some regression slides, and we'll pick out the Durbin-Watson statistic table. The F statistic. And here is a Durbin-Watson table. And the Durbin-Watson statistic I mentioned in the last class, the Durbin-Watson statistic produced by your regression analysis should fall within this sweet spot. Okay? That is, it should be lower than 4 minus the lower limit, table limit, and it should be above the lower limit, lower table limit. So what we need to do is look up the lower table limit for our model. So if we looked at the Durbin-Watson statistic, and we have two variables, right? And we look at the lower limit, the DL, And we have probably 100 some observations. So if I looked at the Durbin-Watson statistic for that, the lower limit would bring me someplace around 163. Does everybody see that? Let me see how many observations we have. The way you can tell that pretty easily, it's 1 plus whatever the degrees of freedom you have under the analysis of variance table. So we have 104 observations. So we have to max out that table in terms of the number of observations. Look down the side, it's over 100. So we're right here. And we have 2 K variables, 2 continuous variables or 2 variables. And it gives us 163 that we have to be greater than. Remember, the lower limit now is 163. We have to be above it to be in the sweet spot. And we have to be below 4 minus 163, which is, let me get the calculator out, 4 minus the table value of 1.63. We have to be less than 237 and greater than 163. Okay, this is 4 minus the lower limit. Okay, so that defines a sweet spot for us. And lo and behold, what we've got here is a situation where a Durbin-Watson statistic is not in the sweet spot. It's well below the 167. So we have something called positive serial correlation. When you're below the lower limit, positive serial correlation means that the residuals have too much cycle error in them. That means this model is not picking up business cycles very well. If it were above 4 minus the lower limit, it would probably mean that we have too much seasonality left in the data. Well, anyway, let's see what we can do about this. So this is a bare bones model. We know that both of our variables qualify, they're significant, the VIF factors are low. We're explaining about 78%. But since this Durbin-Watson statistic is low, lower than the lower limit, which means we have positive serial correlation likely caused by business cycles in the residuals, model residuals, it means that we cannot be 95% confident in the model results. Okay? Doesn't mean we can't use a model because it did not affect the calculation of the coefficient values. Okay? So coefficient values are calculated correctly. Just means that we can't be confident in the model. It's not using the information reliably. All right. This includes the other variables as well in the model. The other variables being the dummy variables that we set up for seasonality. Let me show you. Stat, regression, fit regression model. So let's put those dummy variables, since they only have 2 values, a 0 or 1, we call them categorical variables. They fall under the name of whatever the variable happens to be. In this case, it's Q1, Q2, and Q3, because I left Q4 out, okay? If I put Q4 in, it would leave it out anyway. The reason why is because it cannot solve for an identity. So you can't have a mirror image dummy variables, or you cannot have all the dummy variables explaining all the possible outcomes. You have to have some reason, some degrees of freedom for it to make calculation errors. Okay, here we go. This is the model we get. Bang. And what's happened to the R square value in the F statistic? F is 185, R square is a 78.16. And now the F value fell. Why? And the R square is 78.6. It stayed basically the same, didn't it? 78.16, 78.6. It increased a little bit. Why did the F value fall? The more variables you add to an equation, it has a tendency to drive down the F statistic. Okay? And if this gets too low, below perhaps 13 or around 15, the model is not relevant to the data. Okay? It means it doesn't fit the population very well of the data series. So, did we manage to get one of those dummy variables, seasonal dummies, to be significant? Yes, we did. Q3 is significant, and that means we can use the other two dummies. Dummy variables for seasonality are the only variables that are treated as a group. Any other dummy variable or a variable you have has to be standalone. But since these are treated as a group, if one of them passes as being significant, the entire group, the Q1 and the Q2, can also be used. Okay? So that means you don't have to drop these out. You can keep them in for the seasonal effects. All right. What else can we do for this model to try to improve it? And let's see what happened to the Durbin-Watson statistic. We took the seasonality out, and man, that baby is bottomed out. Look at that, 20.237690. It's really bad. Let's see if we can bolster it a little bit by including some sort of information. Let's look at a time series plot of the data, the Kellogg's revenue data, and see if we see any specific things we want to try to pick up in this model. Well, we have a couple things. We have a data drop here, and then we have an increase, and then at an increasing rate, and then all of a sudden it starts dropping down again. So let's create a recession dummy to pick this drop off here. So let's pick this 89 observation, and all the way to the end of the data series, that's 104 observations. From 89 to 104, we're going to put ones in to designate a recession. And we're going to fill the rest of the data series with zeros. So here again, we're going to create a recession event. So this will open up a column. We call it recession. And actually, it's not the recession. If you look at 89, where that occurred, observation 89, it was actually after the recession, well after the recession. 89 is 2014. So maybe people became health conscious, diet conscious relative to sugary. Let's put a diet effect. Just don't call this a recession. Let's call it a diet effect. Okay. So we start with 89. And we put ones in for this diet effect and take them all the way to the end of the data series. And we call this type of situation a persistent dummy variable. That means it continues on. And if I had to develop a forecast for it, I would put ones in for the forecast as well. All right. Now we need to fill in the early parts of this with zeros. So fill in the first 3 or 4 cells with zeros, and grab the corner, make the little plus sign turn to a small plus, and drag it down. Drag it all the way down to where the ones are you've got. You ought to be able to see the ones pop up. They're the ones. So we'll drag it right here, and you get 0 fills. So it's 0 fill. There's no event, no dietary recession or whatever we're going to call it. And then After that, there's a dietary recession. Let's see if we can add that diet effect into the model and see if it's significant. Go to regression, fit regression model. And we're going to call this, I've already got it there, it is a diet effect. It's also a dummy variable. So it takes on ones and zeros, right? So it's a categorical variable. So we'll put the diet effect at C7, column 7. We'll put that in and rerun the model. Bang. The F value went down again. That's because we added another variable. Adjusted R-square went up a smidgen. And the diet effect is not significant. Look at this. It didn't come out to be significant. So I can't use it. The reason why it's not significant is probably something else is explaining that downturn. So we need to eliminate that from the model. Let's adjust it a little bit and rerun it and see if it influences it at all. Let's adjust it 2 periods. Rerun the model and see what happens. That's all it did is adjusted those 2 points. It should be able to run it. F value R-square is okay. It didn't work. So I have to take that variable out. Just nuke it. Bang, it's out of here. So delete it. Let's just clear the cells because I want to put something else in there. Let's look again at our model or our data series. We had a drop off here. And this could have been a scare due to some sort of problem in serial. Let's call it a serial scare. Okay. And we want to invoke that puppy. If we come back to this chart, it's 36 and 37. We want to make sure this serial scare is in because that's when it occurred. I'm not at the top of the data series, am I? It would be a good idea to go to the top of the data series. If I can get this little X to change, just go down to 36. Come on. I'm not holding my mouth right. I'm running out of, I use a mouse and my little pad is giving me a fit. Come on down to 36. It's down to 35. And then 36 is right here. Make that a 1 and make 37 a 1 as well. And then I follow that up with zeros. Now this is a non-persistent dummy variable. That is, it turns on and then turns back off. Let's go all the way to the end of the data series. Okay. So we just have that serial scare in 36 and 37. See if we can find it here. There it is. Run the regression again. Stat. Regression. Fit regression model. And now I'm going to put Kellogg's And we want to put employed people and interest rates, right? And we wanted to put 1, 2, and 3 seasonals, and then put the serial scare into as seasonal as a categorical variable. Let's see what happens now. F value is not too bad since we improved the model. Now we got 80. Let me roll this down so you can see it better. The F value is a little bit higher. We don't have as many variables in it. The R squaring improved. And the serial scare worked. Okay. But it knocked out our dummy variables. So we might need to go back and put in Q4 to try to. You guys forgive me because I don't have time to go back and create put Q4 in as a variable. Or do I? Yeah, I do. I could just create a Q4 forecast, couldn't I? Let's go back and change the variables then. The dummy variables for seasonality. So we'll have 1. Hopefully, I'm going to take the Q2 out and put Q4 in. See what happens now. Q4 didn't work either. Made it even worse. So what I would do is not use the serial scare. Because what it's done is it took out some of the seasonality, made it non-significant. Although this is pretty close, this 1.4. I tell you what, if you guys get the t-value this close, 1.94, I will accept it for the seasonal. Okay? Is everybody listening to me? And you hear that? Okay. There's something else you could do for seasonality. And that is you can run, go to stat time series. I'm going to tell you guys this, and go to decomposition, and you can run Kellogg's revenue through decomposition with a seasonal length of 4 and store the seasonals. See this little seasonals? Those are the seasonal index. Okay, and when you run it and store it, you get what I've got here. Let's get rid of this junk. It's definitely got seasonality, doesn't it? You see this seasonals? That's where I got that. And let's use this as a continuous variable because it's not described as 1 or a 0. It's continuous. It has any number of digits, any decimal location. And let's see if we can put that in the model instead of the seasonal categorical variables. So this goes regression. So what I'm doing is borrowing the seasonal index from decomposition, and I'm going to put that seasonal index right up here with the continuous variables. Seasonals 1. And then I'm going to take out these categorical variables and just use the serial scare. Oh, Lord, have mercy. Let's see, serial scare. Here we go. F statistics good, 82%. We've got the seasonals that are significant, and see if the seasonal scare is significant too. Yeah, it is. So you guys have a chance of using either the seasonal dummy variables, or you can run the revenue that you've got for your company through decomposition and get the seasonal index. They're called Cs. Okay? In this case, the seasonal index is significant. You guys see that? In our model. So where the individual seasonal dummy variables didn't work very well, that seasonal index seemed to work fairly well. And we also have the seasonal scare, or a serial scare, and we have the 882.66 R-square value. Let's look at the Durbin-Watson statistic. It stinks, doesn't it, at 0.207328? Now, what that means is we're not picking up all the cycle pattern. And if we looked at the data that we've got, cycle pattern is in employed people and interest rates. Suppose we squared interest rates. I know that's cyclical. Let's look at graphs of both of those. Time series plot of both of those variables, X variables. Let's look at the interest rates, employed people, and interest rates. Let's look at both of them. It's got a lot of cycle. This has got a lot of cycle. I tell you what, I'm going to square employed people. I'm going to try to enhance the cycle associated with it, okay? There's a reason why I'm doing that, because it tails up at the end, and it might keep me from having heteroscedasticity, which we'll explain later. Okay? So I'm going to take the employed people, since it's upward sloping, and I'm going to square it, and it's going to give me this. Insert a column, call it square and employed people. Okay? Go up to the calculator function and just have some fun by putting the square root of employed people, populating that with employed people times employed people. Okay? We get large numbers. See the scientific notation? So we move that decimal point 16 places to the right. All right, what we need to do now is rerun the model with that enhanced employed people. Instead of employed people. If I left employed people in there and used the squared employed people, I'd create a multicollinearity. So let's use the squared of the employed people in the seasonals and see what happens. Hold your mouth right. F statistic looks okay. 83% now. The coefficients look like they're all significant, and the signs look correct. And the Durbin-Watson statistic, boo, 206. See this? It's 206 compared to where we were, 207. What can you do? Somebody tell me. Can't you do just the opposite of squaring it? Take the square root. See what happens if we do that. So since SQRT, let's just nuke the values in this column. Okay. I didn't get them all, did I? Okay. So let's take the square root now of employed people and put it there. It's a much smaller number, right? Go to the calculator function. And we're going to put this in square root of employed people. And we're going to take the SQRT, parenthesis, employed people, stick it in there, close the parenthesis up, and bang, there they are. And let's run that now and see what happens. See if we can raise the Durbin-Watson statistic a little bit. Regression, fit regression model. I got to go populate it again. Cal logs. Square root of employed people, interest rates. And we wanted the seasonals in there. And we wanted the, where is that? Oh, here it is, serial scare. That didn't go there. It's a continual a categorical variable. Serial scare goes right down here in categorical. Remember, it's ones and zeros. Here we go. Bang. Still looks good. 82% we're explaining. Durbin-Watson statistic went up to 207 from 206, right? We've done all we could. I'm not messing with it anymore. What does this mean? It means that I'm leaving a lot of cycle out of the data series, but what has happened is I've lost 95% confidence in the model, okay? I can't be 95%. It might be 80% or something less than that, but the model and the forecast, I can't be 95% confident in because of positive serial correlation. That is, the residuals have too much cycle in them. In fact, let's go back to that model, that regression model, and let's save the residuals. Go to storage. Save the fits and residuals. Fits are the model estimate of the data we put in it, and the residuals are, you know what they are. So we'll just do that. Let's take a gander at it, see what it's doing. We're getting a lot of stuff over here. The last two fits and residuals are the ones we're interested in. I'm not sure. Good grief. I'm really going to have to nuke some data, aren't I? Residual 6. Let's get rid of all of that stuff. Redo this one more time. Okay. Let's redo it and save the fits and residuals. Stat, regression, fit regression model. We got the same stuff we had before. Go to storage, fits residuals, say okay. And there we should have them. There they are. All right. Let's look at the residuals and see if they have cycle in them. We could go to time series plot and look at them. That would probably show cycle. But we could also go down to autocorrelation functions for the residuals and look at them with 50 observations. Do you guys see the cycle in this? I don't think we've got too much in terms of seasonality, but I think we do have a lot of cycle. You see it? So that's why the Durbin-Watson statistic is so low. In fact, if we wanted to, I could do a time series plot of the residuals. That's what I started to do anyway. And you could see that those babies have a very strong cycle pattern in them, don't they? So the regression analysis is not lying. It's leaving a lot of cycle pattern behind. Okay? Everybody's still with me, aren't you? All right. So we know we have positive serial correlation. You can see it clearly in the cycle pattern with the ACFs. Let's look to see if we've got something called heteroscedasticity. You guys know how to spell that? Look it up in the slideware. You don't know heteroscedascity, something like that. Let's insert a column between the fits and residuals. Okay. And what I'm going to do is I'm going to come back to that because I want to forecast first before I do that. I'm going to forecast. But we're not going to forecast using the dummy variables, are we? So I can nuke these forecasts. I can clear those cells out. But I need the seasonals forecast, right? Don't I? Do you think? And I need a forecast for what other variable? And then we have the serial scare. I can't spell serial to save my neck. You know what I mean. Oh, I'm not going to put any serial scares in. I don't think we're going to have another one. You could if you wanted to, but I'm going to leave one out. Okay. Seasons forecast. What can we do to this seasonality repeats itself, doesn't it? Right? If you'll note, the seasons simply repeat themselves. Here's the first period, and the first period repeats down here. And then it repeats again, doesn't it? Okay. So where did we wind up? We wound up with the 12th. So we need to start with the first period and capture 2 years of it. So let's just capture the first year and then capture the second year. Okay. Control copy. The seasonals forecast. Oh, come on. Where's the reverse? Why is it doing that to me? It's doing a cotton picking. Control copy. be. There, I got it. I must have had my cursor up in the label or something. Anyway, these seasonals are just repeat year after year. So you need to find out where you left off, and we left off at the 12th period of 2017, and we pick up at the first period of 2018. So it just keeps repeating. All right, let's see what kind of forecast we get. So we got the serial scare, the seasonal forecast, the interest rate forecast, employed people forecast. We should be able to come up with forecast values. Here we go. We've got a good model run. We know we've run a regression, right? We know we've got a good model regression run. Okay. Now, what we have to do is go stat, regression. Instead of fit regression model, which we've already done, we go to predict. Guys, got that pathway? Emily, you see it? See the pathway? You go to predict. And what it does, it opens up the predict menu for you. Okay. And there's the variable that you're forecasting, Kellogg's revenue. And enter the columns of values. Do it. Pull it down and say enter columns of values. You don't want to enter these variables one number at a time. Enter the columns. So now we have to find the forecast for the square employed people. Do we have that? No, we don't. Because we have employed people forecast, but we use the square root of what did we say? Square root of the employed people in the model. So what I have to do is I'm going to have to create that same function for the forecast. Square root employed people forecast. Okay. And how do you do that? You just take the square root of that and place it over here. Let's do it. Go to calculator. We're going to place this in the C14, which is the square root of employed people's forecast. And we're going to take the square root SQRT, employed people's forecast, and select OK, and that square root should appear there. Now we should be ready to rock and roll. We have all the variables we had in the basic models. You get the square root, the interest rate, seasons, and the serial scare. Interest rate, seasons, and the serial scare. All right, let's try it again. Go to stat. We've run a regression model, so we know the regression model is running well and looks good. We go to predict. Okay. And since we check to make sure that you're forecasting Kellogg's revenue, don't enter columns of values, pull it down and select enter columns of values. And that allows you to choose the columns you want. Square root of employed people. I need a forecast of that. And there it is. Here's a forecast for square root of employed people. Interest rates. There it is. Interest rates forecast. Seasons forecast. There it is. And serial scare. I didn't put one in, so it's all zeros. So we ought to be able to store the predicted fits, that's the forecast values, and the confidence limits. Just store those two things, okay? Predicted fits, which happens to be the prediction of the forecast values, and the confidence limits. So the 95% confidence limits around that forecast. Ready? So you press the button, say okay, and let's see what we get. We know we can't rely on the thing from the standpoint of serial correlation. I'm going to eliminate redundant fits and residuals. So let's just delete those cells so it all moves over. So this is the forecast values that we've got, predicted fits. Okay, I could change the title of that and call it forecast. Right now I'm going to control copy that, and I'm going to place it right beside and just below. I'm going to open up a column here. Insert column right next to the Kellogg's, and I'm going to call this regression forecast, REGFCST. And I'm going to paste or Control V those forecast values right after the end of the actual Kellogg's revenue. Here it goes, Control V. There it is. So if I plot this and plot this, we should have the actuals and the forecast. Here we go. Stat, time series plot. Multiple, because we're using multiple columns, aren't we? Select OK for that, multiple columns. When we want the Kellogg's revenue, column C1, or C2 that is, and the forecast, regression forecast that we just calculated. And this is what we get. And if I wanted to, I could just select that line up there and connect the last observation of the data with the first observation with the forecast values. Okay, and that is it. What do you think? Does that look reasonable to you? Yesenia, Kristen, Zach? Does this look reasonable? I would say it does. Yeah, it does. So these are the forecast numbers that we're going to use in our strategic plan for this company. Okay? Yeah, I think it looks reasonable. You know, we can make it bigger so you can see more of the variation, see the nuances associated with the seasonality, but you've got it all there. Okay? All right. So what do we need to do now? Oh, we have to check for heteroscedasticity. What is that nasty word? Let's see if I can type it on this thing. This is, I think, how you spell it. Heterosc. Scedastis. You see it? And what does that mean? Let's get a plot of the residuals. What do you note about these residuals as you move out over time? They increase in value over time in terms of the variation. It's hard to tell, isn't it? Typically, it's called the megaphone effect, and you can tell graphically, but this is very difficult to tell whether or not you've got heteroscedastic results. Heteroscedasticity means that the errors, the amplitude of the errors increase over time. You think this does or not? It's hard, very difficult to tell. There's a test we're going to run for it. to tell whether or not we've got it, okay? And why are we interested in that? I'll show you in a bit. So what we need to do is take the fitted values Did I save the fits and the residuals? Whoops. Yeah, they are. You see the fits and residuals? And what I want to do is open a column up beside each one of them. And I'm going to call this one the squared fits. What we're going to do is amplify the fits by squaring them, as we're amplifying the variation. And I'm going to do the same thing, squared residuals. Get the cursor over there, SQ resids. Okay. And how do you get the squared fits? You go to the fits and go to the calculator first. Squared fits. See if I can find that column right here. Square. We're going to put the answer in squared fits, and I'm going to multiply fits times themselves. Multiply fits times fits. Fits asterisk fits. Bang. And do the same. Now what we've done is amplified the variation with this. Now let's do the same thing with the squared residuals. Go to calculator. We're going to amplify those residuals. We're going to put this into squared residuals. And we're going to take the residuals, just multiply them, asterisk, by themselves. And there we've got the amplified residuals. And notice when you square them, all the signs change to positive. All right. If you've got heteroscedasticity, that is, if the error is going to increase over time, that means that whatever error you have calculated for the model in terms of RMSE and MAPE will not hold if it's heteroscedastic because it's going to be underestimated. What we're going to do is look at whether or not the squared fits, that's the model estimates, are good predictors of the error terms. And if they are a good predictor of the error terms and the model is heteroscedastic. You ready for this? Is everybody ready? Go to regression. We're going to have to run a really simple regression. Fit regression model. Take out all the variables. Shouldn't be any variables left. And we're going to use the squared fits as the continuous predictor. If I could find squared fits, that's right here. It's a continuous predictor of the squared residuals. Does it forecast error? Does the model forecast error? If it does, we're in heteroscedastic. We've got a heteroscedastic model. The only thing I want you to look at in that very simple model is the F statistic or the T statistic relative to squared fits. You see it? What's that coefficient value? That's 2.45, right? Is that greater than 1.960? Somebody tell me yes or no. Is that significant? That means that the model estimates are a significant predictor of the error terms, which means that the model is heteroscedastic. So what does that mean? It means if I calculated MAPE and RMSE, which I will do, from the residuals, right? And no, these are not the residuals. These are from that this clear cells. That's from that last little model run. That's from the heteroscedastic model. Let me see if I can clear cells. There we go. If I can take these residuals that we got from our model and calculate MAPE and RMSE from them, let's try it. Go to calculator. We're going to put this baby in MAPE. Find the MAPE column. Take the absolute value of the residuals. Okay. Divide those residuals by the original data. Slash. Did I put the slash in there? Original Kellogg's revenue. I'm on the wrong side of the. No, let's start again. Apologize. Take the absolute value. That's the first function that you've got. Of the residuals. Divide them. I had the cursor in the wrong spot. That's why it happened. By the original Kellogg's revenue, that gives me percentage error. Sum those percentage errors. And divide them by, what was it, 104, something like that? You guys remember? What was the number that we had? I think it was. And so our MAPE is 11.25%. Let's see, yeah, it's 104. There, we got it right. That's pretty high MAPE, isn't it? Pretty high. It's double digit. That's not too good for a company. But it's good enough for this class, isn't it? Let's see the RMSE. Let's calculate that. I'll put this in RMSE. And it is residual squared. Sum of the squared residuals. Divided by 104, that's to get the average. So that's the mean squared error, and you take the square root, SQRT, of that whole mess. So you can close it in parentheses. And this is our RMSE, which is pretty high. Okay. I'm going to tell you something. Stat time series plot. Of the residuals again. It being heteroscedastic, it means that the variation of this data series is going to get worse and worse. Okay? At the error terms are really averages for the model period. Okay? They're averages. And what's going to happen as the variation of the residuals increase? What's going to happen to that average? Is it going to be exceeded? Yes or no? Heteroscedasticity, once you've discovered it, it means that the error terms that you calculate, the accuracy measures, are going to be exceeded over the forecast period. Everybody got that? Hopefully you do. Okay. One last thing. You also lose confidence, 95% confidence. We lost it already, right, in Durbin-Watson statistic and positive serial correlation. We can't be confident in the model either because of heteroscedasticity. And worse, the error measures that we calculate, the accuracy measures, will not hold. They'll be exceeded over the forecast period. That's not good news. One last piece of analysis for the forecast. That's this forecast, the p-fits that we got. We have the upper and lower confidence limits. C-lim's lower, C-lim 1 is the upper. Let's plot them. Stat time series plot. And we're going to multiple columns, of course. Let's plot the p-fits forecast with the lower limit and the upper limit. Okay, does everybody see that? I'm just choosing C23, the forecast values of p-fits, and the limits, the lower limit and the upper limit. And select OK. And it gives me this little number. And you see the forecast values kind of going down over time with a little bit of seasonality in them. And the limits stay relatively constant, don't they? And don't say the forecast looks good because it falls within the limits. These limits are calculated from the forecast itself. And what you need to be aware of is whether or not this interval between the forecast limits and the forecast itself either increase or decrease over time. So the confidence you have in this model for the forecast period remains relatively consistent. That interval remains the same. Sometimes you'll get an interval that will actually spread apart as you move out over time. That is, spread apart from the forecast. And when that interval starts spreading apart, it means you're losing confidence. So your confidence level is not going to change for the forecast because the limit interval remains the same. Okay? But you can't be 95% confident in it. You have to be some lower level of confidence. We don't know what that is, by the way. Okay, has everybody got it? So this plot will tell you whether or not the forecast, whether you got confidence in the forecast. If you see those limits starting to spread apart, it means that your confidence is going to fall. Everybody had enough for tonight? I think we've covered just about everything we covered last time, if you guys have ever had a chance to look at it. Anyway, give it a shot. I'll upload it as soon as it's transferred, Kristen. What happens is the software that they have mushes it around or does something to it, and I will upload it as soon as it's available, okay? I promise you. Okay, I'll look at it again tonight before I go to bed. I'll look at it first thing in the morning, okay? There you go. Well, actually, the YouTube source, Zach, should be under the content, should be listed under the content. There's video links. It should be down there. That's where the YouTube source should be. So check there and see before you have to email it, okay? Okay. If it's not there, you can email it to me. That's fine. So I'll see you guys. Good luck. Get these doggone company forecasts done. Okay? And check it for what? Check the confidence or the reliability of the variables. Check the VIF factors for multicollinearity. Check the Durbin-Watson statistic for positive or negative serial correlation, and check the KB test that you'll find in the doc sharing that we ran tonight using the squared fits and squared residuals to determine heteroscedasticity, okay? And you've covered the basis on the model if you do that, okay? You can stand in front of anybody with a master's degree or any training in econometrics, and you will look like a champ. Okay? We'll see you guys. Good luck. Push this stuff through to get the money shot, the company revenue forecast. We'll see you. It can only be done with regression, remember. Bye-bye.